All right, in this video, we're going to talk about the force of tension. And in your guided notes, please be following along with your guided notes. You're supposed to write down the definition for tension. Tension is the force present in a rope, wire, string, or cable. Force of tension. And tension is the force that's present in a rope, wire, string, or cable. Okay, a taut rope or wire or string or cable has a force exerted on it. And let's go through this free body diagram. You don't have this in your guided notes, so look up here. Say this was a light hanging from your ceiling, your kitchen ceiling. A lot of houses have a light that's hung, and you have this, a wire, a cable, or a chain sometimes there. How would you find now? If it's a rope, string, wire, cable, we call it the force of tension. I always just put a capital T for tension. Okay, so that's what I will do. How would you find the force of tension here in this rope, string, wire, or cable? How could you find it? Well, here's the key to most tension problems. Is this light that's in your kitchen, is it moving vertically? Is it moving up and down? No. So what does that tell you about the forces that are acting on it? They have to be balanced. So is there a force that we know going straight down? Yeah, that's the force of gravity. Or sometimes some physics textbooks will call it weight. Can we find it? Yeah, we simply have to know its mass. And then we times it by 9.8. The acceleration due to gravity. And that gives you some number in newtons. Well, what is T going to equal? The same number. If this was 10 newtons down, what is tension got to be? 10 newtons, because the forces have got to be balanced, because the object is at rest. Remember Newton's first law? An object will remain at rest, just like this light is remaining at rest, unless you put a net force on it. Well, we want it to be at rest, so the forces have got to be balanced. Okay? And so that's the key to most tension problems. I've got some practice problems here for us to go through. Let's do practice problem number 4. It says a 5 kilogram ball is suspended from the ceiling by a rope, as shown below. What is the force of tension in the rope? Okay, here's the ball. It has a mass of 5 kgs. It's being hung from the ceiling by this rope. What do we call the force in that rope? Tension. So we're just going to label it capital T. Please put that. Capital T. Now, we know that the ball is just suspended from the ceiling. So that means it's not moving vertically. It's at rest vertically. So is there a force that's pulling that ball down toward the center of the earth? Yeah, gravity, or this time I'm going to put weight. How do we find it?
The mass
times 9.8. Good. Hit. What is the mass? 5 kg. So let's plug in here. What's 5 times 9.8?
49 newtons.
49, and yeah, it's a force, so we put newtons. That's 49 newtons. Now, is this object moving up and down?
No.
No, it's at rest. So what does that tell you about the forces that are acting on it? They're balanced. So what does tension have to equal? 49 newtons. Okay. So how easy is that? Okay. Finding tension. Now it can get a little more complicated. Let's look at some practice problems that are a little bit more complicated than that. Practice problem number 5. It says the same ball, a 5 kilogram ball, is suspended from the ceiling, this time by 2 ropes. So this one's got 2 ropes. What is the force of tension in each rope? Okay, good. This is a rope and this is a rope. We're going to call it tension in both of them. Let's call the one on the left T1, and let's call the one on the right T2, just to kind of differentiate the two. Now again, is this object moving vertically? No, it's at rest vertically. So that means the forces acting on it are balanced vertically. What's the force that's going straight down? Force of gravity, and it's mg. Again, the mass is 5. G is always 9.8 on Earth. So that's, what is that? Again, it's 49 newtons straight down. Well, if the forces are balanced, whatever the force is down has to be the total force up, right? So I've got a total force of 49 newtons going straight up. But this time I've got 2 ropes.
Divided by 2.
So 49 is equal to 2t. How do you get t by itself? Divided by 2. Tension is equal to 24.5
Yep.
newtons. So T1 would be 24.5 newtons, and T2 would be 24.5 newtons. Guys, tell me about, why would they do this? In the real world, why would you put 2 ropes on an object?
Maybe one can't fit it all.
Yeah, what if this object is really massive and it has a lot of weight, and it could break 1 rope? What could you do? Put 2 ropes on there, and what does that do to the tension force? Cuts it in half. What if I would have had 3 ropes here? Divided by 3. Okay, does that make sense?
Yeah.
And so that's tension. Let's look at a little bit different scenario here with practice problem number 6. Okay? Practice problem number 6 says, determine the tension in each cable. Hint, there is more than one way to define the system. I want you to label this tension in this cable T1. T1. And let's put this one as T2. Now I want you to think about this one on your own. I'm going to hit pause. I want you guys, if you're watching the video, to hit pause and try it on your own first. See if you can solve for tension 1 and tension 2. And then hit play and see if you got it right. Okay, let's see if you guys got this one right. It says the hint, in the hint there's more than one way to define the system. So I want to kind of point that out. I think it's probably easiest to solve, it doesn't matter, but I think it's probably easier to solve for T1 in this case. When you think about the tension in this rope, what mass is contributing to the tension in this rope? It's only the 4 kilogram. Would the 7 kilogram mass be contributing to the tension in this rope? No. So let's define the system as this now. So we've just got one mass of 4 kgs hanging. We're looking for T1. How do we find the force that's going straight down? Force of gravity. How do we find it? mg. What's 4 times 9.8, guys? 39.2 newtons. Now, is this object moving up and down? No, it's at rest vertically, so that means the forces need to be balanced. What does T1 have to equal then? 39.2. Okay, how many of you guys got that for T1? Okay, good job. Now let's define the system a little bit differently. If we look at the tension in this rope now, T2, what mass is contributing to that? Both of them, because this one's pulling down on it, and so is the 4 kilogram one. So if we define the system this way now, okay, I'm just going to draw one big mass. What would the total mass be that's contributing to the tension in this rope? 7 plus 4 is 11 kgs. Okay, so if we find the force down, which is weight, is mg, what's 11 times 9.8? Sorry, what is that? 107.8 newtons? Okay. Now, again, it's not moving vertically. It's not moving up and down. So that tells me that this tension, which we called T2, has to be equal to what? Okay. They have to be balanced. So these forces have to be balanced. So how many of you guys got that the tension in T2 was 107.8 newtons? Good. Can we see that now, though, how that works?
Yeah.
Hope so. Okay, now we're going to get into some more complicated problems where we use tension at an angle. So if it's at an angle, what do you think we're going to have to use in order to solve for that force? SOHCAHTOA. Okay, we're going to use trigonometry. So this is where, if you haven't watched the trigonometry video, please go back and watch that and review trig, and then we'll better understand how to do this problem. But let's get started, okay? Practice problem number 7 says a 5-kilogram object, here it is hung from 2 ropes as shown below. Find the tension in each rope. Okay, so here's the one rope, and here's the second one. Okay, now are they going straight up and down? No, they're being hung at an angle of 30 degrees, so theta is 30 degrees. But it wants us to know the tension in each rope. So let's label each rope T. Okay. I'm going to call the one on the left T1 and the one on the right T2, just to kind of differentiate the two. All right. As always, what's causing the tension or the force in this rope? Yeah, it's the weight of this mass right here. So let's find its weight. The weight is equal to mg. Okay, what's the mass? It's 5 times g is 9.8. What's 5 times 9.8, guys? 49 newtons. We've done that one before. 49 newtons. Okay. Now, if that's the total weight down, is this block moving vertically? No. So what does that tell us about the forces? They have to be balanced. So everything up. So right now we have 49 newtons down. What does everything up have to be? 49 newtons. But the complicated part about this problem is that tension is not going straight up, is it? It's not. So we need to find the component of tension that is going straight up. And so it's not obvious here, but we can use trigonometry. But if we want to use trigonometry, what do we have to have? A right triangle. Do you guys see a right triangle there? Two of them. Hopefully. Okay, let's just draw in these sides. They're not there really, but we're going to draw them in, okay, with the dotted line. If it doesn't actually exist, most physics textbooks will have a dotted line showing the sides of those triangles. Okay. Now, what we're going to do here is take the tension force and divide it into its component parts. Do you guys know what a component is? It's a part of the whole, right? It's a part of the whole thing. So one part of this tension force is in the y-axis. One part is in the x-axis. So here's what most physics textbooks will do. They'll say that this is tension in the x-axis. So they call it T sub x. And this is the same thing, tension in the x-axis. Now, what do you think they call this other leg? T sub y, for tension in the y-axis. And this one will also be tension in the y-axis. Okay? So yeah, it wasn't a triangle, but we can draw one in to make it work. Okay? Now this is a right triangle. It's a right angle here. So we can use trigonometry. Now what component of the tension force is going straight up and down? Ty. So how many Ty's do we have? 2 of them. So if the total down was 49 newtons, what does each Ty have to be? Okay, let's do that. 49 is equal to 2 Ty's. And if we want to solve for Ty, what do we have to do? Divide by 2. So Ty is equal to what? 24.5 newtons. And so now we have a side of the triangle, 24.5 newtons. And this one's, let's just put it right here, 24.5 newtons. Okay? Now with trigonometry, if we want to solve for a side, we have to have at least one side. We've got Ty. And you've got to know at least one angle. We know the angle is 30 there. So can we use trigonometry to solve what the tension is? Yes. So let's write this down. I know we're still reviewing some trigonometry. Let's write SOHCAHTOA. SOHCAHTOA. Okay. Now, if this is our angle, this is theta right here. What side do I have? What's Ty? Opposite. And I'm trying to find The hypotenuse. So which trig function has opposite and hypotenuse in it? Opposite hypotenuse. Okay, we're going to use sine. Okay. So let's write that down. Sine of what was our angle again? 30 is equal to opposite, which is 24.5, divided by the hypotenuse, which is tension. I'm just going to call it T. Now, how do you solve for T? I really don't like it on the bottom, so how do I get it off the bottom, guys? It's times both sides by tension. Okay, over here, tensions cancel out. Now I want to get tension by itself. How do I get rid of this sine of 30? Divide by the sine of 30, both sides. Okay, and so tension in this case will equal 24.5 divided by the sine of 30. What is that?
49.
Yes, perfect, yeah. So tension is equal to 49. And is it a force tension?
Yeah.
Yeah, so what are my units going to be? Newtons. Okay. Now, that's going to be the tension in each one of these. This one's 49 newtons, and this one's 49 newtons. This was an interesting problem because the weight was 49. So if you're going to hang something with ropes at an angle, there's even more force of tension in those ropes at an angle than straight up and down, isn't there?
Yeah.
And sometimes in the real world, you literally can't go straight up. When they hang something across Main Street, can they put something straight up?
Yeah.
What are they going to hang it to? There's nothing there. So sometimes you just can't, and so you put it on an angle, but you better make sure that your rope, string, wire, or cable is strong enough to hold the mass that it's hanging. That's hanging, right?
Yeah.
You wouldn't want it to fall on some car as they were going by, right?
No.
So, good idea to do some physics on that first, right?
I was thinking about that.
What a good way to figure that out. Okay, we were right. 49 newtons in each of those ropes. Okay, I've got a couple more. Practice problem number 8 is just almost exactly the same kind of concepts as in practice problem number 7. I'm going to hit pause. You guys try it on your own. Please try it first and then hit play and see if you got it right. Okay? So give it a shot. Okay, let's see if you guys are on the right track here. It says a traffic light is supported by 2 wires. Okay, here's our 2 wires. One right here and there's one right here. As shown below, if the maximum tension in each wire is 750, so this is 750, and this one is 750, and the angle between them is 80 degrees, that's what it shows right here, and the horizontal component is 482 newtons, what is the maximum weight of the light that they can support? Okay, so these city workers have these cables. They know that the cable can support 750 newtons of weight. They're trying to figure out what's the biggest light here that they could hang from there. How much mass would they be able to support? So let's figure this out. Here's kind of the key to this problem. It says the horizontal component of that tension was 482. The horizontal component goes left and right. So if we draw in our triangle here with the dotted line, that horizontal component, this, what do we call that? Tension in the x-axis is equal to 482 newtons. Guys, I'm going to do it on one side. Wouldn't this side be exactly the same?
Yeah.
Okay, so I'm just going to focus on that right side. Okay, now we have a right triangle. Okay, so hopefully you've made it to this point. You have this right triangle. but we don't have an angle here. Can we figure out what that angle is? Okay, if this, how many degrees is a straight line, guys? That's 180 degrees. If we've already got 80, what's left? 100. And we've got two of them, so we're dividing it evenly. What's this angle going to be? 50 degrees. Okay, so let's put...
You use Pythagorean theorem too.
Okay, you could use Pythagorean theorem to solve for this side. But let's use trig.
Okay.
Yeah, let's use trig.
You insist.
But yeah, you're right, Rylan, you're right. Okay. Now, how do we figure out weight, guys? Weight is equal to mg. How could we determine this? Well, if everything down equals some number, what does everything up have to equal in this case? That same number, because this light is not moving up and down, it's at rest. So whatever the total force up is, that's going to be your total force down. And so we really need to find this component of tension, Ty. Okay? So let's solve for Ty using trigonometry. I want you to write this down. So, ka, toa. Now, we need the opposite, and we have the hypotenuse, and we have adjacent. What trig function do you want to use, guys?
Toa.
Do you want to use TOA? Yeah. Okay, let's use it. So tangent of 50 is equal to opposite. What was opposite? Ty divided by adjacent. What was our adjacent side? 482 newtons. Okay. Now, if we want to get Ty by itself, what do we got to do? Times by 482. Okay. Over here it cancels out. So grab the calculator. 482 times the tangent of 50. What do you guys get?
574.
Yeah, I'm getting that Ty is equal to 574.4 newtons. Okay, let's put that in my free body diagram over here. 574.4 newtons. Okay, now the key. If everything up equals everything down, what's the total force that's going straight up? Would it be just 574.4? Or are there two TYs? There's two of them. So let's times that by 2, and that will give us the total force that's going up. So 574.4 times 2. Do you guys see why we're timesing it by 2?
Yeah.
1,148.8 newtons. Okay? That's the total force that's going up. So if the total force is 1,148.8, what's the total force down got to be?
Off by 1.
1,148.8.
Yeah, not even.
Okay, so we know the weight, guys. I'm going to solve it up here. If the weight is equal to mg, and the weight total that you can support with those two cables is 1,148.8, that's equal to m. We don't know the mass. That's what we're trying to figure out. Do we know g, though? 9.8. Okay. How could we get the mass by itself? Divide by 9.8. I'm sorry, Cole, what was that? 117.2 newtons. Someone else verify that?
Kilograms.
Oh, yes. I was seeing if you guys were awake. This is a mass, so that's kgs. Okay? Okay, so that's our answer. The largest mass would be 117.2 kgs. That's our answer. But guys, it did ask for the weight. So the maximum weight, 1,148.8. But guys, hey, if you were the engineer on this project, would you recommend the city buy a light that weighed 1,148.8 newtons?
Heck no, 1,000.
No, why not?
9. Danger.
Then you have to add on the gravity.
Because what if the wind blows? Is it going to kind of sway it? And if it adds 1/10 of a newton, is it going to then move? Yeah, it could break these wires here, these cables. Would you want to give yourself some leeway? My point is, would you want to give yourself some leeway?
I
Yes.
trust in Japanese class.
So I would recommend that they buy a light that weighs a little bit less than that, right? Okay. We don't want to max it out. Okay, how we doing, guys? Are we doing okay? And yes, we got it right. That was the same number as here. So good job. Okay, we've got one more problem. You up for it? Let's finish it. Let's finish strong. Okay, practice problem number 9. Hey, this is going to be a typical, I'm going to put this one right on the test, right here. Okay. A man pulls a 50-kilogram box at constant speed across the floor. Okay, I'm going to underline what it gives us. 50 kilograms is the box, mass of that box. Underline constant speed. What does that mean, guys? Please put balanced forces. Right there. He's pulling it across the floor at constant speed. He applies 200 newtons of force at an angle of 30 degrees. What is the force of friction? We're looking for the force of friction here. Okay. Let's draw our free body diagram onto this diagram here. Okay. What was the mass of this box? 50. So please put that, 50 kgs. He's pulling what looks like a rope. What do we call the force in a rope?
Tension.
Tension. Please put that. Did it say how much he was pulling? 200 newtons. So the tension is equal to 200 newtons. Put that in. Okay. At an angle of 30 degrees, what is the force of friction? Okay. Which way is friction going to be pointing, guys?
That way.
To the right. So on this box, to the right, we're going to put force of friction.
Parallel to the surface.
Yeah. What force is going straight down with this box?
Gravity.
Yeah, force of gravity or weight. How do we find it? mg. So let's do that right now. What's 50 times 9.8? 490? 490 newtons, okay? Now, is there a force that's going from the ground up?
Yes.
The force that the ground puts on the box? My point is the box moving up and down in a vertical manner?
No.
No. So this normal force has got to be what?
490.
Or does it?
Nope. Guess not. Because he's pulling up on it.
Yeah, oh. This is a good problem because look, isn't there a component of this tension that is also going up? So we're going to call this one Ty. Guys, isn't his lifting up at an angle going to take some of that weight off of there? Yeah. So we need to find Ty. What we do know though is that everything down equals everything up. And everything up is Ty plus the normal force. It's Ty plus the normal force. Everything down is going to be the weight. So let's use trig here. Guys, I need an opposite and I have hypotenuse. Which one should I use? So let's do the sine of 30 is equal to, what's the opposite? That's tension in the y direction. And what's hypotenuse? 200. How do I get Ty by itself? Times by 200. What's 200 times the sine of 30?
100.
So Ty is equal to 100 newtons. Okay, let's put that in. 100.
Turn off my
Here.
phone for that.
Hey,
Sorry.
okay, if Ty, which is going straight up and down, is 100. So now we have Ty, so I'm going to put that in 100. plus N is equal to the weight. Can I make an equation here? What I'm saying is everything down has to equal everything up, but going up there's Ty and there's normal force. So can't we say that weight is equal to Ty plus the normal force?
Yeah.
Aren't they equal? Okay, let's plug in. What was the weight? 490 is equal. What was Ty? Ty was 100 plus the normal force. How do you get normal force by itself? Subtract 100. That becomes what? 390 is equal to the normal force. Now we can put that in right here. 390. Do you guys see why it's not the full 490?
Yeah.
Can we get a sense of that? Because this guy is pulling up, and which is taking some of that weight off of. So the ground doesn't really feel 490 newtons of force. The normal force is going to be 390. Okay. Now that we have all of the forces, hey, now that we have all of the forces, or do we have all of the forces?
No.
Nope. Let's solve for Tx.
Force applied.
Because here's why. Constant speed tells us the forces are balanced, right? In order to find that the forces are balanced, won't I have to know what force he's pulling straight horizontally? And then that will be equal to the force of friction? Let's see, I don't know, maybe we can do it another way. But how would we solve for Tx? It's the adjacent and we have hypotenuse. What's adjacent and hypotenuse? Isn't it cosine?
Yeah.
Of 30 is equal to Tx over 200.
200 cosine of 30.
Times by 200.
173.2.
So Tx is equal to what, Cole?
173.2.
173.2 newtons. Okay. So this is 173.2 newtons. Okay. Now, if we know that, guys,
Force of friction is the same.
if we know that he's pulling with 173.2 newtons to the left, straight to the left, friction has got to be what? 173.2. So let me write it over here. Force of friction is equal to 173.2 newtons. Wow, that's a good problem. Isn't that a good problem, guys? That is. Okay, let's see if we got it right. I hope that we did. Yeah, the answer, exactly what we got. Okay. Okay, good stuff. Look how much you guys have learned in one day. I'm impressed. Okay, we're going to spend some time now with some, I want to give you more practice with these tension problems. So there's a worksheet in the student workbook. It's called the Force of Tension worksheet. Please go there and try those problems. Force of Tension worksheet. And I hope this video helped you.